Hi everyone. So I'll be doing question 62 from page 126 in our textbook, and it's basically 3 parts, all about limit proofs. So this can be found in the chapter 2 review exercises. So we're going to start with A. Assume that f at x is less than or equal to L for all x near A, and the limit as x approaches A of g at x equals 0. Give a formal proof that the limit as x approaches A of f at x times g at x equals 0. So we can take the bits of information from the question. Assume that f at x is less than or equal to L for all x near A is telling us that the limit as x goes to A of f at x equals L. That's what we can take from that section. And then we also know that the limit as x goes to A of g at x equals 0. Now, assuming that these two conditions are met, we can use them to prove that the limit as x goes to A of f at x times g at x equals 0. So because limits follow the product law, we can split apart this limit into 2 different parts. So we can express it as the limit as x approaches A of f at x multiplied by the limit as x goes to A of g at x equals 0. So now we're basically given the 2 parts we need to solve this, so we're just going to put them in. So this piece is going to go into here, and this piece is going to go into here, and we're going to get L times 0 equals 0. So any real value multiplied by 0 is going to return a 0. Therefore, the limit as x goes to A of f at x times g at x is going to equal 0. So now for question B, we have to find a function f for which the limit as x approaches 2 of f at x times x minus 2 does not equal 0. So the problematic piece is this one right here, x minus 2, because as x approaches 2, this piece goes towards 0. Now we're assuming that f at x approaches 2 is going to return a real value, and then it's going to be multiplied by 0, as in the first question when L times 0 equals 0. But we can actually eliminate this 0 by making sure that f at x has a denominator of x minus 2, and then those two can cancel out. So technically the whole piece wouldn't exist if we were just plugging it in by substitution, but the limit would still exist as we're approaching a real value. So we have the limit as x approaches 2 of f at x times x minus 2. As long as our value of f at x has x minus 2 in the denominator and does not have another x minus 2 term in the numerator, the limit will exist. So we can write this as f at x equals the simplest one, 1 over x minus 2. This doesn't violate the result stated in A because of the fact that we're canceling out the other x minus 2. So this is going to give us. Then when we simplify this whole thing, we're going to get and this is going to cancel out, giving us. Now the limit of a constant term always returns the constant term. So this limit is going to equal 1, which is not equal to 0. Because this term is technically undefined, the function, I guess we can call it g at x equaling x minus 2 over x minus 2, doesn't exist at x equals 2. It doesn't mean that the limit doesn't exist. So then, for our final question, we have the Heaviside function is defined as h at x equals a piecewise function, and explain why the limit as x approaches 0 of x times the Heaviside function equals 0. So we're going to have to take cases for this question. We can't simply split it apart in this kind of way, the limit as x goes to 0 of x times the limit as x goes to 0 of the Heaviside function, because the limit as x goes to 0 of the Heaviside function doesn't actually exist. If we look at the graph of our Heaviside function, we have that when x is less than 0, our function equals 0. And when x is greater than 0 and equal to 0, our function equals 1. So when we look at our two-sided limits, as the Heaviside function approaches 0 from the left, the limit is 0, and from the right, the limit equals 1. So these two do not equal each other, meaning that the two-sided limit does not exist. So therefore, we can't multiply a given value, this one would equal 0, times a limit that does not exist. So we have to actually look at this in more depth. So we can distribute the x into the piecewise function. First, let's write out the Heaviside function, and then use this to figure out what x times the Heaviside function is going to look like. So this is going to look like 0 when x is less than 0, and x when x is greater than or equal to 0. Now we can take our two-sided cases. We're going to look at the limit as x approaches 0 negatively of x times the Heaviside function. So that's when x is less than 0, right here, and we can see that it equals 0 up until the point 0. So we're going to say that this equals 0. And the limit as x approaches 0 positively of x times the Heaviside function, when we look at this, we see that it equals x when x is equal to or greater than 0. So in fact, this hole that was created gets plugged up and just becomes the line x. So we can see, as we look at our function this way, it's approaching 0. So now we can see that the two-sided limit exists as x approaches 0 of x times the Heaviside function, and that it equals 0. So that's it for my question. Hope this was informative. Thank you for watching.